So what we left out there is dimensionality reduction, right? I threw out the keyword dimensionality reduction. Does anyone want to talk about it? Any idea what you think it might be? Like, huh?
Like, from what I understood, what he said, it means that you are trying to cap off the dimensions at a point where accuracy is at its peak.
Good, good, yeah. Anybody else wants to add to that?
And each dimension is a specific variable you have.
Very good, good. Okay, so let's take off from there. So do you want to, so let me just say that aloud. Tell me your name.
Sharon.
Shayon. Okay, so Shayon said, what we had talked about there, that we try to capture that sweet spot somehow. The goal of dimensionality reduction is to see at what number of features, when we cap our model to kind of taking as inputs, what number of features, that sentence did not make a lot of sense, but at what number of features we're getting that sweet spot where we have maximum accuracy, so most bang for the buck, right? And we kind of want to cap it there. So there are two reasons we want to do that. One is there might be a slight fall in accuracy, right? So accuracy drop, potentially. Are you guys taking notes? It might be a good idea because I like the way we're kind of moving in continuity, and this might be a good pitch for people with no ML background, right? So I'm kind of making up my own storyline, so this is kind of good. The second thing is there's actually a cost to increasing the number of dimensions, right? What do you think crunches all the models? Computation, right? So as you have more number of dimensions or more features, the computational complexity of the model may increase, right? So in my lab, we do a lot of stuff to decrease the computational complexity of the model, right? And actually a byproduct of that is we might even increase the interpretability of the model. Right? So we actually started with one potential thing, and I'll come to that, right? So let's just try to systematically go first layer, go hierarchically. I actually like that word. Some of these words are tongue twisters. Hierarchical is actually hopefully going to come by the end of this class, because I told you this is a little bit of a special class where I kind of just got to know the background of my cohort. So I'm kind of trying to set the lay of the land. So I'm going to try to have this word come back in a different context today, hierarchical. I think that'll be this introductory class might be a good point where I should actually introduce that in the kind of purview of a new kind of model, right? But what we're trying to do in general, the approach for today's lecture is we will go one level of depth, and then we'll go and dig into it further, right? So these are the three things that might happen if you have a lot of features, especially when there are redundant features, right? So if you have too many redundant features, there might be an accuracy drop. You're increasing the computational complexity without really helping your modeling process, and you're potentially decreasing the interpretability, right? If you have too many dimensions. And this is basically what is the curse of dimensionality, the dimensionality curse. And you will see this come up a lot. So these, I'm not making these up, right? This is technical lingo for ML stuff, right? So the curse of dimensionality, you'll see will come up a lot. And one of the reasons we have dimensionality reduction algorithms is to kind of circumvent the curse of dimensionality, to come to a number of features that is not doing any of this, right? Not resulting in accuracy drop, not increasing the computational complexity. Now, what happens if you increase the computational complexity that is kind of like genotype to phenotype? If you increase the computational complexity, you'll increase the runtime of the model, right? So it might not only be using more resources, you might throw GPUs at it, right? Does anyone know what GPUs are? GPUs are just like very powerful, like let's call it like hardware, right? General processing, graphics processing units. But the reason I mention that is you might need very powerful computational resources to crunch these models, which, at some point now, the field is actually going toward energy efficiency. So it is not going to be energy efficient, right? And we'll see if we can kind of cover that a little bit, because in my lab, we're actually doing this. How do we increase the efficiency of the modeling process, right? So they're increasing the efficiency. So let's actually also put that in, like computational complexity. So we have runtime, and we have efficiency. So let me give you an example, right? Like, for example, if I'm showing you a video, right? And if everyone is just sitting around, right? And if I kind of cut off some of the video, no one's going to really care, right? Whereas if you have like a horse racing thing going on or something where there's a lot of activity, there if I cut off chunks of video, then it's going to be kind of making a difference, right? So there are different ways in which you can actually decrease the runtime and improve the efficiency of different modeling processes. I just gave you a very vanilla example of that, right? The interpretability is because as you have a more complex model, right, as you have more number of features, you might even need a more complex model to actually be able to do the modeling. And sometimes these more complex models are not as interpretable as the less complex models. So again, I'm going to throw something in here. And it might be a little bit out of context here, but it might help. So if I have a linear model, let's say a linear SVM. I know I have not introduced SVMs yet. And if I have a non-linear SVM. And I'm going to actually, since SVMs are very popular models, I'm going to actually have a particle class just to give you some idea of what an SVM is. Not today. SVM stands for support vector machine. And all I want to, I might actually give you a little flavor of that today. So the difference between a linear SVM and a non-linear SVM is, again, get these words, right? I want you to get comfortable with the lingo. A non-linear SVM is computationally way more complex, may take a lot of runtime, may take a lot of compute resources, may not even run on a CPU. I actually have an example from one of my papers that if you try to run something on a CPU, it's going to take 50,000 years. That is how long Homo sapiens have been there on Earth. That's how you kind of need to have a distributed model, basically in one run, right? So sometimes people think, oh, what is speed up? Sometimes the speed up is required because without that speed up, the model is not even going to run for all practical purposes, right? So by increasing the computational complexity of the model, you might need more compute resources, it might take longer runtime. Sometimes when we're writing papers, we want things to work fast, right? Because in computer science, or applied computer science, you often have deadlines. So if the deadline has come up and we have a quick experiment to run, we might need to speed up things, right? There are various reasons for which you might need to speed up things. But another reason is the efficiency of the model, right? So if you actually do energy measurement, right? If you try to do, okay, what is, say if you have a small device like a Raspberry Pi. I'm going to actually throw that out as a keyword. So that's just a small computer, right? So if you try to run something on a Raspberry Pi, if you try to run something very complex, a very complex model on a Raspberry Pi, firstly, it may not run. Secondly, if it runs, it might take way longer, or it might consume a lot more energy. So again, the machine learning field is going toward more efficient models, right? And one of the things is, remember, this is being recorded. So one advantage is, I think you guys, I'll have to figure that out, but you guys will get the recording as well, right? So it's kind of helpful. So having bite size, you might just have a 20-minute bite and then another 20-minute bite, right? So Raspberry Pi, just consider these as these simple devices, really cheap, like $50, where you can run different simple algorithms, right? So it's computationally less expensive to run things on a Raspberry Pi, right? A very expensive model may not even, when I say expensive, I mean a computationally expensive model may not even run on a Raspberry Pi, right? So we kind of covered why we need a model with not huge number of features. So going back to the Portland housing market example, right? Let's connect it to that, right? So say I found that after adding the fourth feature, my accuracy is like this, or my accuracy is like this, or it basically plateaus. And maybe there are some kinks, right? Now what's the point adding more features, right? You're kind of making the model bulkier, but you're not really getting much bang for the buck, right? So this is kind of what we call the curse of dimensionality. And to kind of beat this curse of dimensionality, there are various dimensionality reduction algorithms, right? And we're not going to cover that today, but depending on how fast and how exciting our course gets, we might even cover some of these dimensionality reduction algorithms in some form in one of our lectures, right? But the most common one is principal component. component analysis. I wish I had more, I didn't think of this. But I'm going to just write it here, PCA. A derivative of that is ICA, but you might see these being thrown around, like if you're reading a paper, they might say, we ran PCA to decrease the number of features in the model, right? So PCA stands for Principal, PAL, Component Analysis. Essentially, at a high level, what you're doing, you're kind of taking the principal components, right? There is a way to do that. ICA is a variant of that, slightly more complicated, but the most common one used is PCA. And this is an example of a dimensionality reduction algorithm, right? So I know I said by the end of this, we'll know where, how the supervised algorithms can be kind of classified into different types. So actually, since I said that, let's kind of change gears a little bit and still use this whiteboard and just get into a little bit of what are the different kinds of supervised learning algorithms. So for now, forget about unsupervised learning. We have not gotten into that. So just to kind of end this part with an intuition of the supervised learning process, right? So remember this term labeled data sets, right? So one of the things that is very helpful to a data scientist is presence of labeled data sets, right? So think of the Portland housing market data set again, right? So if I have lots of houses, real houses, with all their features, right? So say house A has 4 bedrooms, 3 bathrooms, 1,200 square footage, and location is really close to downtown, right? And say it's $1 million. I'm sure it's more than that. I think Portland is really expensive, but let's just forget about the reality right now, right? And the reality is kind of bizarre with COVID-19, so this feels good. Okay, so in the Portland housing market, say we have a lot of these labels available, right? So we have dollar pricing of, say, 150 homes in a data set, right? Now, those are labeled data sets, where I have given you, this is the label. And the label is basically the Y label, right? So let me go back to, and I'm going to actually use a new whiteboard for that, and we'll take a break before that, just like we've been doing. But let's go back to just our, just to kind of start exploring that third topic of the day. Remember this equation we talked about, y is equal to mx plus c, where y is actually the house price, x is the feature, and b, forget about it for now. We'll use it in the next whiteboard. But remember, we have multiple features, so we might have x1, x2, x3, etc. We picked 4, right? So we have mx1, m1x1, m2x2, m3x3, and m4x4, right? And we have clipped off the others by doing PCA, principal component analysis, and we've seen the rest of the features are not that important for the prediction, right? So now we have y hat, which is the predicted value of y, is equal to m1x1 plus m2x2 plus m3x3 plus m4x4, right? And then we have that b, right? So what I was getting at is the presence of the labeled data sets. So think of the model as a person, right? So you're telling this person, right, if this is the value of feature 1, x1, this is the value of feature x2, this is the value of feature x3, and this is the value of feature x4, then this is the price of the house. Not the predicted price, the actual price. So I'm going to throw out another term that comes up a lot, and that's called ground truth. So the presence of labeled data sets is like knowing what the ground truth is. Again, ground truth is something that will come up a lot. It's like basic knowledge for machine learning lingo. And that's why I felt a course like this would be helpful, because, you know, like, it's not common knowledge unless you've gotten into the machine learning area to know some of these terms that are thrown around, right? So I'm going to actually stop there, because my board space is over, and we've actually covered about 15, 20 minutes again. And then we'll talk next about a little more about what is the modeling process like, right? So what are the different kinds of supervised machine learning models, right? So that's going to be the part 3 of our class today.